Let's begin. Thank you for sustaining through the course. We are right at the point where we will start solving the Navier-Stokes equations as promised. 6, 7 lectures. Well, 4 lectures. This is the 5th lecture. Exclude the first 2, motivation and intro. This is lecture number 5, technically. And we hit the milestone, our milestone to do Navier-Stokes with the finite difference method. This is not going to be the method of choice that we will use in the future, because if you notice that my approach has been, I want to teach you how to drive and make mistakes and crash the car and then learn how the engine operates. And I think that's very effective of teaching. It's one way of doing this rather than going through theory, and step by step until you get to the end of the semester and just solve, flow over a point or something silly like that. So we're going to start driving the car. We're going to start solving Stokes with enough ammo that will get us to get stable solutions, and then we'll start digging deeper in part 2 into the details. Now, this will not be the method of choice, but historically it was sort of the method of choice, and people discovered that it doesn't work. And together we are going to rediscover that those issues, why this method does not work. Specifically, it's the finite difference approach on Navier-Stokes. And at this time, at this point, we have enough tools to tackle the Navier-Stokes equations. We know how to do advection. We know how to do diffusion. So we know how to do advection, diffusion. We know the stability limit on those. So the only difference with Navier-Stokes is that the advection term is nonlinear. You have u, v, and that's fine. We just multiply those and do the finite difference approximation on those. And then Maher on Tuesday covered how we can solve a Poisson equation. We haven't seen the Poisson equation yet in the Navier-Stokes. We are going to derive that today. But essentially, we have all the ingredients to get to Navier-Stokes. So let's do it. If we look at the equations in 2 dimensions, and I'm writing them in conservation form. If you recall, you go back to the 2nd lecture, see how we derive the equations. There's multiple forms you see of these equations. Sometimes you might see u du by dx plus v du by dy, and u dv by dx and v dv by dy. That form, you might see it in the literature. It's legitimate, but it assumes that continuity has been satisfied. Because if you take these terms and you do the chain rule, you can extract a continuity equation out of them. And then you say, oh, continuity, du by dx plus dv by dy is 0. I'm going to cancel out those terms. I am of the opinion that you shouldn't do that. And my opinion is true in this case. You shouldn't do that because numerically, you cannot guarantee that your continuity equation has been satisfied. And we will demonstrate today, actually, that we will not satisfy the continuity equation despite all efforts we will make. So if you keep it in this conservation form, in the way it contains that error that you would have introduced in the continuity equation, it is a better general, this is the conservation. Everything is under these derivatives. It's easily integrated, and you can think about it in a clean way as everything is under that derivative term. I divided by the density over here, so 1 over rho dp by dx and mu over rho. Now density, we will assume density is constant over here. So we will just call this term mu over rho, just call it nu, kinematic viscosity, and 1 over rho, we can absorb rho into the pressure. So you can drop that term and absorb it into pressure. It becomes a modified pressure. And as you will learn, numerically, the pressure is really a meaningless quantity. It's not the pressure anymore. Only the pressure gradient is what will matter to us. We will see that the pressure is only acting as an auxiliary variable, as a scalar, that will allow us to satisfy this equation. Now, if you remember, we have 3 unknowns here, u, v, and p, correct? And we have 3 equations, x momentum, y momentum, and continuity. And if you've been following what we have been doing, we think about transport equations as a time derivative, advection, diffusion, and some source term. These are advection, diffusion, source term. And you advance the equation in time for the quantity that's under the time derivative, right? So we say that the x momentum We can't use it to solve the pressure. We will use it to solve the u velocity, right? Because it's the quantity under the time derivative. We're going to advance that in time. Same thing for the y momentum equation. We will use that to advance the y momentum or the v velocity. This one is not a time-dependent partial differential equation. We cannot advance it in time. It is an algebra. It is a constraint. Okay, and the only constraint equation that we looked at was the Poisson equation, right? Didn't have time derivatives. It was an equilibration problem. We will show that this equation, we will convert this equation to a Poisson equation for the pressure. Okay, so indeed, we still have this for x momentum, this for y momentum. We will have to work with this to extract an equation for the pressure to enforce this condition. Okay, so let's see how this works. Yeah.
So the reason that you guys are, the reason that we're only considering pressure as a constant?
Not a constant.
Not a constant, what did you say?
Scalar.
Sorry, scalar.
It is a scalar.
Yeah, but so from what I remember from fluid dynamics is that that pressure term is basically responsible for stretching, or I'm sorry, moving a fluid element from one place to another? Some external body force.
Yeah, but numerically, the pressure, this P is meaningless. Only the pressure gradient is going to matter. So we will see as we advance in the course, we will see that when you apply this algorithm that we're going to describe, you are only solving for the average pressure over a time step, not an instantaneous pressure. So when you extract the value of P from our algorithm, you cannot say that that's the pressure at that point. What matters is going to be the pressure gradient, which is the driving force that, is over fluid elements, etc., like you described. It's the pressure gradient that matters, not the absolute value of the pressure itself. So that's the distinction I want you to make here. Because in our algorithm, when I say P, it's really not the same as the hydrodynamic or thermodynamic pressure in a fluid mechanics calculation. It is not the same. It is related to it, but it's not the same. That derivation requires a little bit more of work. We will do it in part 2 of the course. Maybe I'll do a lecture, actually. I was thinking this morning I'll do a lecture on the relation between the P that we will derive in this algorithm today and the actual instantaneous pressure in the Navier-Stokes equations. But they will differ by almost a constant, okay? But they are related. Now, the pressure gradient is the same. So when you plot the pressure gradient, yeah, it will be the same because that looks at the rates of how the pressure is changing in space. Okay. Okay, so we will consider a structured uniform grid for the time being. This will work with non-uniform grids as well. But for simplicity, we will take a structured uniform grid. This is a representative stencil that we will be dealing with, always centered at point ij. Remember, in 1D, we center things at point I, say I plus 1, I minus 1. Same thing here at point ij. We have I plus 1, I minus 1 in this logical Euclidean setup, and j minus 1 and j plus 1. So we do have everything necessary, all the tools we need to solve these equations, starting with the time derivative for x momentum. At point ij, we are advancing the x velocity in time. We will use forward Euler approximation. So we will apply an FTCS scheme on this. That's the simplest scheme. We knew it worked with the advection diffusion equation, gave us second order in space. We're happy with it, first order in time. Let's just apply that on the Navier-Stokes equations. So starting with the time derivative, un plus 1 minus un over delta t, we get that. For the x advection term, you have ui plus 1 minus ui minus 1. So it's a centered scheme over 2 delta x, right? If you can do upwinding based on the advecting velocity. It becomes a special case. Same thing for the second advection term in the y direction. You have vuj plus 1 minus vuj minus 1 over 2 delta y. You're just approximating these derivatives with a centered scheme, right? So we know how to do this, all of this. Finally, for the diffusion term, for the x momentum, it's the Laplacian or the Laplace operator on u, del squared u. It's ui minus 1 minus 2 uij plus ui plus 1 over delta x squared. So this is second derivative in x for u, second derivative in y for u. Okay? And finally, we have a pressure gradient. We will also use a centered difference scheme. So I'm going term by term in these equations to show you that we know how to do all of these. We've done all of them. all right? And for the center difference scheme on the pressure gradient, again, we're centered at some arbitrary point ij, is going to be, for the x pressure gradient, pi plus 1 minus pi minus 1 over the delta, which is 2 times delta x. Same thing for the y momentum. Time derivative, vn plus 1 minus vn over delta t. First advection term, with the u velocity, you have uv I plus 1 minus uv I minus 1 over 2 delta x, and then vv, the advection in v, vj plus 1 minus vj minus 1 over 2 delta y, right? You're just approximating these derivatives as centered derivatives. These are all order delta x squared. Diffusion term for the y momentum. Again, you have two derivatives here, the d2v by dx squared plus d2v by dy squared, right? And then finally, dp by dy, which is the pressure gradient in the y direction. You have pj plus 1 minus pj minus 1 over 2 delta y. Now, notice when I do not mention an index, it means that index is fixed. So when I say pi plus 1 minus pi minus 1, this is occurring at the same j. Okay? When I say pi plus 1 minus pi minus 1, it's occurring at the same j. Or this should be, sorry, this is a typo. This should be pj plus 1 minus pj minus 1 over 2 delta y. It says the same I. Okay, so when I don't mention that second index, it means that index is fixed. Okay, okay, so we're still not done yet because we have no way of solving for the pressure. Now, notice one thing I did in these equations. I did not put a time level for the pressure, right? On all quantities, there's n, because this is an explicit method. Only un plus 1 is the one we're computing, and everything else is in terms of previous values, previous level values at time level n, except for the pressure. Now think about it. If we put n on the pressure, we're going to pick up a pressure from the previous time step. Suppose somehow you have some pressure starting from an initial condition. What do you do with the continuity equation? You haven't solved the continuity equation yet. So really, we don't know what the pressure is. We don't even have a time level for the pressure. In fact, there's a debate on what the time level of the pressure depends on. What is it? Is it n plus 1? Is it n? Is it n plus half? Now, that will depend on the time advance method that you're using. If you're using forward Euler, if you're using an implicit method. But for now, there's no time level on the pressure. And I will keep it that way because that pressure is still an unknown quantity. So over here, we know everything except the pressure. We know how to compute it here, but we need to get it from somewhere else. So let's see how we get it. Go next. If I write everything in discrete vector form, so I'm going to take all of the terms that I represented before, condense them into one vector equation. So if the u vector is u and v, and the advection term is advection for x momentum, advection for y momentum, and the d term is diffusion for x momentum, diffusion for y momentum, just simply condense them into a vector form. And this gradient of p, again at ij. Now notice I put nabla here based on h, which is the spacing, delta x or delta y equal to delta y. So grad h simply means this is a gradient operator based on spacing h or delta x, delta y in this case, okay? So I put everything in vector form here so that we can see what we're going to do with the pressure, okay? Sorry, I need to move this, turn this around so I can see what's coming out next. Okay, so what about dilatation or the continuity equation? So the continuity equation in this case is really just div u equals 0. Which time level should we use for the continuity equation? Is it div un equals 0 or div un plus 1 equals 0? Continuity equation is given to us as just a statement on there's no time derivative in it. But where should it apply? So starting with an initial condition, if your initial condition is divergence-free, then good. But most of the time, it's not. And you really have no control over that because you're kind of specifying it. So, and it's really hard to specify an initial condition that is divergence free. So typically, we specify it as whatever it is. So we specify our initial condition as some initial condition. It might have divergence, so it doesn't need to satisfy continuity equation. If it satisfies it, great, but most of the time it doesn't. So take the problem that we will do next. Is going to be an impulsively driven cavity. So you have fluid in a cavity, and at the top you start moving the wall horizontally. So you have a fixed velocity at the top, say u equal 1 meter per second, and everywhere is 0. Now calculate div u in this flow. You're going to have a non-zero dilatation at the top. The algorithm is going to fix that, but the initial condition, you cannot just let it be. And we really don't care about div un. What we care about, think about it, is un plus 1. We want our new predicted velocity to be divergence free. We want un plus 1 to satisfy continuity equation. Think about it in this sense, right? We want our new velocity that we're predicting to satisfy continuity equation. So that is the essence of these methods that will untangle the velocity and derive an equation for the pressure. There's a few of them. This is called the pressure-velocity coupling problem. There's no equation for the pressure, but the pressure is implicitly specified through continuity. We haven't seen that yet. We're going to see it in a second. This pressure-velocity coupling, there's multiple ways of figuring that out. In the literature, you can read about it. The related artificial compressibility are methods to untangle. They add an artificial time derivative to the continuity equation and advance it in time with the rest of the equations. Pressure projection, which we will learn in this class, and then all the simple time type algorithms, which you would see in COMSOL or Fluent, simple or simple R, simple C, etc., simplex, simplest, etc. This stands for semi-implicit method for pressure-linked equation. It's a version of the projection method. Okay, I don't think it's very clearly understandable, but it's one way of untangling this problem. We're going to learn about the projection method. Once you understand the projection method, you can read about the other ones and understand them as well. They are all related to each other, and they all result in a Poisson equation for the pressure. These two, at least these two. Okay. So let's talk about the projection method. I'm going to go back to this discrete vector form. Now, we still have the continuity equation that we did not use, right? That div u equals 0. And we just said that we want div un plus 1 equal to 0. So what if we take the divergence of this equation? It's a proper operation, right? We can apply a spatial operator on this. So if we take the divergence of this operator, now we've exposed div un plus 1 over here, right? And from what we just said, we want this div un plus 1 to be equal to 0, right? And what also happens, look what happens here. You get this div grad, you get a Poisson term, or you get the Laplacian of the pressure over here. So now we can extract an equation for the pressure from the two momentum equations by combining them with the continuity. How do you combine with continuity? You just take the divergence, and the minute you say, oh, I want this to be equal to 0, you've applied the continuity equation. You can't use it anymore, but that gives you an alternative equation for that, right? That gives you another equation, which is an equation for the pressure. So when you put these two together, and then recall that div un plus 1 is equal to 0, so we knock out that term. And then from this is a new equation, entirely new legitimate equation that is a replacement of continuity. Yes, we reused momentum, okay, but we created new information by applying the constraint div u equals 0. That little thing over there creates an entirely new equation for what? For the pressure. You bring the pressure to the left-hand side, and you derive an equation for the pressure. That's why we were learning the Poisson equation. How to do a Poisson equation. Del squared P equals some source term. Everything here is at level n. Del squared P, we don't know. It's just a value for the pressure. Now, if you solve this equation, you are going to get a pressure. You're going to put it back in the momentum. Remember, in the momentum equations, you have everything at n as we time advance. we still have that grad P. If you solve this term, this equation for P, you put P over there, that will make un plus 1 equal to, div un plus 1 equal to 0. That will make your new velocity divergence free. It's mind-blowing, but yet it's very simple, right? So in a way, this pressure, or keep calling it pressure, this term P, if you solve this equation, this will guarantee that your new velocity is going to be divergence free. Okay? So solve this equation for the pressure, and then use that pressure and put it back over here. So the way to think about this, as you're building your time-advanced solution, you do un, you have it. You compute advection, the advection term. You compute the diffusion term. You come to the pressure. I don't have the pressure. Let's solve this equation for the pressure. You already computed A and D, right? You take their divergence of D. You still need this little term over here. I'll explain it in a second. You solve this Poisson equation for P. You bring P over here. And ta-da, you get a momentum solution that is supposedly going to be divergence free. You can try this for yourself. If you take div un plus 1 over here, you get div un and div a, and del squared p. Substitute. If you solve del squared p correctly, then bring these over here, and everything is going to cancel out so that div un plus 1 will truly be equal to 0. Now, you'll observe that there's this little term over here. It's very important. This term actually accounts for any issues with dilatation in your initial condition. So if your initial condition is not divergence free, this term will account for it. If you don't have this term, you will have a residual error in your dilatation throughout your entire simulation. So this term is very important to carry any errors in dilatation from your previous time steps. Okay? It's very important to derive it this way. Some people derive this algorithm using the continuous differential equations, not the discrete form. If you do it that way, you do not have, you have du by dt. You don't have un plus 1 minus un. And when you apply div u on du by dt, partial u by partial t, you just set that equal to 0. You lose the effect of this term. And in fact, this was an issue in our big code for a while until we figured out how to do it discretely. So here's how the projection algorithm starts. You start with the initial conditions for the velocity and the pressure. Pressure, just set it to 0, always set it to 0. Then you compute all your fluxes, advective and diffusive fluxes, right? So those were the terms that depend on the previous time step. Then you solve the Poisson equation for the pressure. Notice that I'm using the term PPE. This stands for the pressure Poisson equation. So when we say solve the PPE, that immediately implies this is the pressure Poisson equation. It's a Poisson equation for the pressure that makes a velocity vector field divergence free. Okay? And then we do the time advance. Take that pressure, put it in the time advance, and keep repeating until you're done. Okay. I want to take multiple looks at this because this projection theory is very old, but yet always still in active research. In fact, our group is still doing research in this area, okay, with projection methods. And we do high order time integrators with variable density and reacting flows, et cetera. So there's a lot of debate still going on, a lot of discussion on these projection methods. And I'm active now, at least historically, that could be related historically. So I will call this a continuous formulation of the projection method. And the thought is, if you take the Navier-Stokes equations, their advection diffusion, you have this pressure term, we notice that the pressure term is really tied into continuity. If you only take the momentum equations now and without the pressure, you just have advection diffusion equations on momentum. They are legitimate equations, but they don't represent fluid flow. They represent some process, okay? We call it momentum, diffusion, advection. Sure, it's legitimate. You can solve them. You're going to get a solution, but that's not divergence-free, okay? So here's the process, a continuous process that represents that procedure. So if you were to think about the Navier-Stokes equations as advection diffusion of momentum without pressure, and then the pressure is an additional effect to make them divergence-free. Could we do this? Yes, there is math that we can use to prove, to demonstrate that you can do this. If you treat Navier-Stokes as advection diffusion processes without satisfying mass conservation, then you bring the pressure and extra this free parameter that allows you to readjust those vector fields to make them divergence free. Turns out, yes, there's a process in math that allows us to do this. Here's a formulation that does that. So I'm going to rewrite the Navier-Stokes equations as partial u tilde by partial t equal minus advection plus diffusion. Notice I put u tilde here because this u tilde is some velocity that is not the true fluid velocity that satisfies mass conservation, but only contains advection and diffusion. So this process computes a velocity field that does not conserve mass, and numerically it would look like this: u tilde n plus 1, etc. The same procedure. Everything here depends on u, which is fine, but it doesn't have pressure in it. And you can compute this without continuity, but this u tilde does not satisfy mass conservation. Okay? Then you take this process, you say du by dt equal minus grad p. You're adding this pressure gradient term, but notice what du by dt is. Du by dt in this case is the difference between the true velocity and the non-mass conserving velocity. Okay? So when you combine those two together, they give you the previous equations. They give you the previous differential, the discrete form and the previous form that we had. Okay, they give you those. So if you take u tilde and you say u tilde is un minus delta ta plus, you plug it in, it gives you this form we saw earlier. Okay? So now why does this work? It comes from a procedure called the Helmholtz-Hodge decomposition. Do you have a question? No. Okay. All right. And this procedure says that a well-behaved vector field can be decomposed into an incompressible rotational vector and a compressible irrotational component. Now, if you did your vector calculus, and if you took fluids with me, you remember when we said when two vectors are parallel, then their cross products is 0. When two vectors are perpendicular, then their dot product is 0. Now, if you were to treat nabla as a vector operator, that will have implications on curl and gradient. Okay? So the Helmholtz-Hodge decomposition says that you can take any vector field and decompose it into what I call a perpendicular component and a parallel component. This is the incompressible component that is rotational, so it has rotation in it, but incompressible, so div u perpendicular is 0. And this is compressible. It means it has dilatation, but it is irrotational, so the curl of this one is 0. The div of this one is 0. The curl of this one is 0. Very important theorem. So look at this. Okay. So this would be the incompressible component, and this would be the rotational component. So let's see how this relates to Navier-Stokes. If you treat nabla as a vector, then what this theorem is saying is that any vector u can be decomposed into two components. One component parallel to nabla and one component perpendicular to nabla. So this treats the nabla operator as a vector. Okay, I always like this to think of nabla as just a vector, So if you think, although it's an operator, but if you think of it as a vector and draw some arbitrary vector u, the Helmholtz-Hodge theorem says if u is well behaved, doesn't explode at infinity, or there's no singularities, etc., then you can decompose this into a component that's parallel to nabla and a component that's perpendicular to nabla. This immediately means when you think about vectors that are parallel and vectors that are perpendicular, it means that the cross product of u parallel and nabla is equal to 0, and the dot product of u perpendicular and nabla is equal to 0. Okay? Now, when the curl of a vector field is equal to 0, what does that imply on the vector field? Irrotational. It is potential. It's a potential, right? It's the gradient of a scalar. Okay? It is the gradient of a scalar. So in other words, you could say that any vector field is an incompressible component plus the gradient of a scalar, any well-behaved vector field. Okay, bear with me, we're almost there. For the Navier-Stokes equations, this would imply that your non-mass conserving velocity field that u tilde that I showed you earlier, that provisional velocity field that only comes from advection diffusion, if you want to make that, so forget the second equation in that slide. If you only take the advection diffusion terms in the Navier-Stokes equations without the pressure, call them u tilde, to make them divergence free, this is what you need to do. You say, I'm going to take this one that's not mass conserving, and it's going to be equal to a mass conserving vector field plus the gradient of a scalar. That scalar is just simply essentially that pressure. That's how that works. So you don't really need that other equation at the bottom. You solve the advection diffusion equation for without the pressure for u tilde, and you write this down. Now, this will help you derive an equation for the pressure. So let's see how this means, what this means. Okay, so again, going back to this one, if you take the divergence, so actually, let me do it on this one. Sorry. If I do it on this one, if I take the divergence of this is not 0. Divergence of this is not 0. But we know by definition that the divergence of this is 0. So that gives you the equation for the pressure. This will give you that del squared P is div u tilde over delta T. Or in other words, if we go back to these guys here, if you take the divergence of div of un plus 1 and set it equal to 0, then you get the relation between del squared P and this provisional velocity field, this intermediate velocity field. This intermediate velocity field is only contains only the advection and diffusion parts of the Navier-Stokes. Okay? We're almost there. For now, we will look at simple boundary conditions. Okay, so this is going to be our algorithm. Advection diffusion are going to be the easy parts. Once we get to the pressure, we'll look at the equations again and put that together, and we'll get the solution. We will also need boundary conditions. For now, we'll only look at the case where the velocity components are specified at the boundaries. So in other words, you could have, if u and v are 0, it means you have a wall. If the wall is moving, impermeable, so no flow coming through the wall, so it could be moving, sliding like the driven cavity, then u dot t, which is the tangential vector on the wall, is equal to some u wall. U dot normal equal to 0. If this is 0, then it means it's a stationary wall. And this implies also that the pressure must satisfy a 0 Newman condition at the boundaries. Because if you think of the pressure as a term that corrects the velocity to make it divergence free, if you know the velocity, you don't need a correction. Okay? So if you go back to that equation, let me go back. If you go back to this one, if you go back to this equation, and you think about the pressure as a correction to u tilde that makes the velocity divergence free, well, if you know the velocity, then you don't need a correction. So this must be 0 by definition at a boundary where you know the velocity. And this will imply that u tilde and u are the same. We're not going to care about that because we'll only implement boundary conditions on u. Okay? So that implies for velocity specified boundaries, it always implies that the Newman boundary condition on the pressure is 0 at all wall boundaries. And that's why Maher covered Newman for the Poisson, because we need to approximate those at all boundaries. Now, if you've taken PDEs, you know this. If you haven't taken PDEs, the Newman conditions on a second derivative are a problem because your solution will only be specified up to a constant. So if you integrate, let's say you're integrating d2t by dx squared equals 0. Okay, or equal to some constant, right? So you're going to get constant times x. So you integrate first, and you integrate twice. If you only have boundary condition on dt by dx, you still have a floating constant there that cannot be specified. Okay, and that will lead sometimes to your solution diverging, because the iterative solver cannot converge. It's floating by a constant. So what you do, you go and fix that constant and say, I know the pressure at one of the boundaries. And the trick here is very simply, where was that? should have been here. Sorry. Looks like my slide did not sync. So we will specify a value for the pressure at one of the boundaries to fix that constant. And that's just fine. So when we do the lid-driven cavity problem, we're assuming either a wall that's moving the fluid or there's air blowing on an open cavity in your car, right? So say this is atmospheric pressure. My P is 0. Just set P equal to 0. That will get you to a unique solution. OK? All right. So forget these slides. All right. So this is what the problem that we will do. We will do a lid-driven cavity. It's going to be a 1-by-1 cavity equal aspect ratio, stationary walls everywhere except the top wall. It's going to be moving at a fixed speed. And the boundary conditions that we will do are these. The axial velocity at the top wall is specified as u wall. V is 0, so there's no flow coming in. U and V 0 here. U and V are all 0 everywhere. The wall, so there's no slip. U is the tangential component of velocity is stuck to the wall, and it's impermeable, no flow is coming through, and also Newman conditions everywhere. But like I just said, that because then your pressure is going to float because of this constant, your solver might not converge. We're just going to put P equals 0 everywhere over here. Okay? For stability, we will take our 2D conditions that we derived last time, Courant and Peclet numbers. In this case, now you have the Reynolds number, because the Peclet number is for scalars, the Reynolds number is for momentum, right? It's the same thing, Vd over nu, right? And so it's the same thing as the Peclet number. I'm just going to call it the Reynolds number here. So if you do the operations over here, you get these two conditions on stability. Delta T must be less than this, and delta T must be less than that. So we're going to compute these two quantities and take the minimum. We will just do this at the beginning of the time step using the maximum speeds that we have, okay, which is the U wall that's driving the flow, okay? And we'll set that time step as fixed for the entire calculation. You can do adaptive time stepping in your simulation. You can do a check if you want, but we're not going to do that. All right, so let's get our notebooks ready. See, we got plenty of time. And I'll go back and forth with these slides. We have pretty much all of the ingredients. I'm going to copy and paste most everything from, so if you had your notebooks all done before, excuse me, then you can just copy paste from over there. All right. Let's I'm going to create a new notebook. Window. And let's call it in class Navier-Stokes Finite Difference Method. Okay. And I'm going to make this a little bit bigger. Let's see. Can you guys see in the back? Okay. And I will get the boilerplate stuff. I hope you already have all of that. Set up NumPy, Matplotlib, all the good stuff. Okay. So I'll first kind of hard code the advection diffusion terms, then we'll create functions for those because we haven't done that before, but we are evolving as we code this. We are evolving together and learning how to do things better and better. Okay. So let's start by declaring, so declare some problem spec. So Lx is equal 1.0. This is a cavity of 1 meter by 1 meter. Okay, meter. All right, we will do 32 grid points in X and 32 grid points in Y. And we declare the lens space. Again, I need the X and Y lens spaces if I want to plot things nicely. Lens space going from 0 to Lx with an x point. And that helps me define dx, x1 minus x0. And y is mp.lens space, 0 to Ly with ny points, and dy is y1 minus y0. And we can do a mesh grid, p dot mesh grid, x and y, right? You can verify things are good. Lt.im show xx, okay, yep, and yy. Everything looks good. Excellent. Okay. Let's define conditions on the conditions and flow properties. U wall is 1.0 meter per second, so that's top wall velocity, and nu, which is mu over rho, kinematic viscosity, just I don't know, 0.05, doesn't matter. Now we'll do stability conditions. So we will just do one. In practice, you might want to do this. You will want to do this at every time step. Check your time step size. Or you can take like the worst case scenario. In some problems, there's no acceleration going to happen, no faster flow that's going to happen beyond the driving speed here, which is the wall velocity at the top, right? So you can just set that stability at those conditions, worst case scenario, and just use that time step. Okay, we will do this. Okay, so let me move this here. So we had dt. So we had two rules, stability conditions. dt1 was equal to 0.5 over nu or mu, or let's call it nu. Okay, so over nu times 1 over delta x squared plus 1 over dy squared. Okay, make sure you don't mess up the parentheses here. Okay, so that's my from rule 1. And rule 2 was 2 nu over u squared plus v squared. And now what is your u squared? It's u wall. That's the maximum worst case scenario you're going to get, right? So u wall squared times u wall. And I don't have any y velocity component, so I'm not going to set that. Okay? If you want to be more conservative, you put another u wall times u wall, you make v equal u wall, but you don't need that. It will still be stable. And then dt is the minimum of dt1 and dt2. And you can print dt and gives you print stable time step size is dt, and that's in seconds. Oops, I need a quotation mark here. Yep, it's 0.0052 seconds. Second. Now these conditions are for a Reynolds number. If you've taken fluids, you understand that the Reynolds number is going to determine what flow regime you're in. Are you laminar or turbulent? And you will see as you push the Reynolds number on this problem, you will start observing more and more recirculation zones in the cavity. So when you look at this again, what should we expect? You're driving this wall. This wall is in contact with the fluid, so subsequently it's going to move the fluid. As the fluid moves, it's going to hit the wall here. It's going to turn because of mass conservation. It turns, and it's going to hit the wall at the bottom. It's going to turn, hit the wall over here. It's going to turn. And it's going to spin and create this primary vortex. But also at the corners, here, here, and here, you might develop other rotational structures as well. And those will depend on your Reynolds number. Okay? And as the aspect ratio changes, you might break up this primary vortex. There might not be enough inertia for the flow to sustain one large vortex. Okay, so you might have more than one. All right. So those are the dynamics of the problem that you can explore with a properly implemented CFD code. Okay. All right. So we can print in the Reynolds number here. Say Reynolds is U wall times Lx over nu. So that's the Reynolds number based on the top wall, and it's at 20. Okay, it's pretty low, very laminar, nice, easy flow. I don't want to deal with a turbulent flow because this method, if you don't have, if your resolution is so low in time and space, we're not going to be able to capture turbulent time scales, and your solution is going to go unstable. Okay, so we would have to either refine our grid so much to capture all the turbulent structures or model them, which we haven't. We're not going to do either of those. Refining will cost a lot of time, and modeling, we're not even close. Let's learn how to walk first, okay? So we will deal with this simple laminar case. All right, so let's declare some arrays. We'll start with the U velocity component, mp.zeros, and did we learn in this class? It's nice. It's more convenient to index in the last dimension first, z, y, x. So we're going to index in y and x. So we'll declare these arrays as ny and x. In this case, it's not going to matter because nx and ny are equal, but it will make a big difference when you go to non-uniform grid spacing. Again, for v velocity, also ny and x, note that I don't need to implement any ghost points at this point because my velocity, I have velocity nodes or velocity variables right at the boundary, right? So I can just set those over there directly. If I had Newman conditions, which we don't because we said we're going to deal with specified boundaries, we are going to have a Newman condition on the pressure, but we will do what you learned on Tuesday. We're going to use an interior stencil to get that Newman condition. So we don't need a ghost point to make that Newman condition work. We will just use points from the interior. So we're entirely contained. Okay, with this, that's one of the nice advantages of the finite difference method is for Navier-Stokes is that that concept of ghost points can be entirely eliminated. When we go to staggered grid, it's really hard to do without ghost points when we do finite volume methods. All right. Now, let's also do an initial condition for P, and P.0 is just an initial array. And we will say that this is ny and x as well. Excuse me. OK. All right. We should be ready to do the time advance now, and we'll start plugging in the pieces as we go along. Time advance, t equals 0. We're starting from t equals 0, t end. Let's say 100 delta t, just to me. We're going to do 2 delta t so we don't get stuck in an infinite loop or something, okay? And then while t less than t end, the first thing I like to do is say t is equal plus equal delta t. So just increment your time, okay? All right, so we will first start by setting the boundary conditions. You can set the boundary conditions here, or set them inside the loop at the beginning or at the end of the time advance. it doesn't matter. Set boundary conditions on velocity. Okay, so we'll start with the top wall. Okay, we have for the top wall, we have u equal u wall and v equals 0. We haven't said anything about the pressure because we will handle the pressure in the pressure Poisson equation solver separately. So top wall, so this boundary conditions on velocity. We want all the u components of velocity at the top wall to be equal to u wall. So what does that mean in our indexing? That v, okay, at the top wall, which is at -1, right, for the y-axis, for all x points is equal to u wall. Sorry, u. u -1 in the y indexing, so that gives us, remember, we're indexing logically like in Euclidean grid. J equals 0, 1, 2, 3, blah, 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 all the way to the end. So we're going to start at the end, say that u at this j value, which is -1, for all x values is equal to u wall. Okay? It's equal to u wall. Same thing for v at -1, and then for all x values is 0. So top wall. Let's do, why don't you do the other ones? Why don't you guys do the other ones? Okay? Bottom wall, u and v are 0. So where's the bottom wall at? u 0, all x equals 0, and v 0, all x equals 0. Okay. Right wall, now we're changing in x. We have to just change the indexing. So u and v are equal to 0. So u for all y at the right wall, which is -1, index in I, that's 0.0, and v, all y values, -1, equal to 0.0. So that's the right wall. We're taking the last index in the x direction. And finally, on the left wall, first index in x, so this would be u semicolon 0 is equal to 0.0, and v semicolon 0 is equal to 0.0. Okay? So we have two equations to integrate here, and for each equation we have x advection, y advection, x diffusion, y diffusion, and then a pressure gradient. So we'll focus on advection and diffusion first because we know how to do those. So we will start with the x momentum. Let's build the right-hand side. So you'll notice here how I'm thinking about things differently, because I have this gradient term that I can compute. I compute all the advection and diffusion terms, right? And that pressure the pressure Poisson equation depends on the divergence of the advection and diffusion terms. If I build the right-hand side of momentum without pressure gradient, that's going to give me the term needed for the pressure Poisson equation, advection and diffusion, right? So we'll start with x momentum. We build the right-hand side. I'm going to call this u right-hand side. And that's going to involve these terms here. Okay, we need 1, 2, and 3, 4 terms here, the 2 terms in the diffusion space, right? Okay, so now if you've done this, we did this in advection. So if you remember in our advection calculation, in our 2D advection diffusion problem, we kind of worked through this, right? We said we did the central, we did the upwind scheme on the 2D advection case. We did the 1D advection diffusion. So we can go ahead and implement this as well for these guys. So let's see how we can do this. All right. I'm going to do it this way first and then say, hey, you know what? How about we make a function for this to make it really easy. So this is going to entail u times u. So we start with this term, convection x, right? So u times u at I plus 1 minus u times u I minus 1. You can do u squared. So you can build a temporary array with u squared, called u squared, and then do the discretization on that. Or you can multiply them on the spot. Let's multiply that on the spot for the time being. So if we were going to do u right-hand side, we're going to start with advection. Let me say Cx is np dot zeros like u. And now my advection term is only going to matter at the interior points, because at the boundary, I am specifying the values for the velocity at the boundary. And if you try to apply the advection term at the boundary, you're going to spill over the boundary. So you need a ghost point, etc. So we need to avoid that. We need to be smart about that. Okay? So the smart way of doing this is we would create like a convection term array. Let me see what I've done here. Okay. Filled with zeros, but then only fill the interior points with the convection term. Okay? So that would just do everything all the way, all the interior points, even the first interior point. The first interior point will need the boundary point, right? Because it's going to be I plus 1, or it's going to be 2 minus 0, value at 2 minus 0, right, over 2 delta x. So it can handle that. All right. Let's do it the hard way first. I'm going to multiply them together. So this is going to be u times u. So it will be u at I plus 1 times u at I plus 1. So what is u at I plus 1? So this is convection, and x we're taking all y, u at I plus 1, which is on the, sorry, this is u, yep, at I plus 1. So it's going from 2 to the last point times u from 1 to minus 1, or you can take the square of that, minus 1, minus 1, and we're going to I minus 1 now. Okay, so that will be convection in x over 2 over delta x. So is this clear? So I'm doing, forget the j index, I'm doing ui plus 1 minus ui plus 1 times ui plus 1, which is ui plus 1 squared, minus ui minus 1 times ui minus 1 over delta x. So I'm doing this term over here. Okay? So that's convection in x. Convection in y is going to be u times v. Well, the x momentum convection in y, right? So this really would be cux for the x momentum, and this would be, and then we would need cuy, which is mp dot zeros, like u as well. Okay, and cuy, also same thing here. I'm going to copy and paste this. Okay, and this would be u times v, or v times u, to be consistent with my nomenclature, minus v times u. Okay, and then you repeat the same thing. But you're going to end up with like 15 lines of code doing the same thing over and over again. So why not create a subroutine that does this for us, right? You just tell it, compute advection for the u momentum with the u velocity. Compute advection for the u momentum with the v velocity. Compute advection for y momentum with the v velocity, right? So we create one function or two functions, one in x, one in y, that does that for us, right? And then it will clean things up. And we will do the same. We should do the same for the diffusion term as well. So how about we create some routines that do that first? So I'm going to declare or create some routines, helper routines to compute first and second derivatives. And I'm using these words, first derivative, rather than advection and diffusion, because it's a property of the finite difference method. When we go and do finite volume, we will name them differently. We will call them convection, flux limiter, upwinded terms, etc. Okay? So some helper routines for first and second derivatives. The way I will implement this is I'm going to assume I have some quantity that I'm advecting, and I'm taking that quantity as the product of the advecting velocity and the advected quantity. So my function is going to take UU or VU, UU or VU or VV, and just going to compute either d by dx or d by dy of that quantity. Okay, just the first derivative of some quantity. Okay, so I'm going to call this d dx, my quantity plus the spacing. That's all I need. I need that quantity, the field, the array, the vector, the array, the mesh points, right? The values of that quantity with the spacing. And we declare result. Result is mp dot zeros like f, which is that quantity. And then same thing, result 1 to minus 1, 1 to minus 1, only on the interior point, is going to be equal. I'm just going to copy and paste this from here. Look what I'm going to do. It's going to be equal to, oops, f I plus 1 minus f I minus 1 over 2 delta x. So now really my cux is nothing more than d dx of u times u, right, with spacing dx. Agreed? That makes sense? So that's duu by dx. It's just going to, once it comes here, this f is going to be uu, and it's going to do the job for me. Now we also need to declare one for y, d dy. I shouldn't have deleted the other ones. That's OK. F dy, same thing on the interior, except I'm going to swap indexing now. Fj plus 1 minus fj minus 1 over 2 delta y. Yes, thank you, Adnan. Good catch. All right. So now when I come here, then I know that my first advection term and then cuy is going to be d dy of v times u with dy. Now check this out. The x convection term of the y momentum, which is zvx, is going to be d dx of u times v, and the x, and then cvy, the y advection term for the v momentum, is d dy, v times v dy, right? So I'm doing just these derivatives, guys, these derivatives. My routines, these 4 lines of code up there, allow me to save tens of lines by just reusing them. Okay, in fact, I'm not going to store them in temporary values. I'm just going to dump them here directly. Okay, so what I'm going to do, my u right-hand side is going to be, if you look at the equations, my right-hand side for u momentum is going to be minus duu by dx minus dvu by dy. I'm going to say minus d dx of u times u, okay, minus d dy of v times u, okay, right? Because that's going to be my convection term. That's the right-hand side of du by dt. Is going to be minus duu by dx minus dvu by dy, right? And same thing for the v momentum. V mom right-hand side is v right-hand side is minus d dx. What do I have? U times v in the x direction minus d dy, v times v in the y direction. So it's this guy, duv by dx, duv dvv by dy. Okay? Now, I don't have to declare an array for these because this ddx and ddy, they're already declaring memory for me here. So u right-hand side and v right-hand side are going to be just the correct size with the correct values everywhere, okay? Now let's do diffusion. So the same way we did a function or a routine for advection, we will do a routine for diffusion, right? And it's going to do this guy. And that routine is just going to be one of them because it combines both x and y derivatives, right? So I'm going to call it actually the Laplacian. And I made a mistake here. I need to return result. It's the same mistake I make every year. Return result. OK. Now I'm going to define Laplacian, again, for a quantity, and dx and dy. So this one, this computes nabla. Can do nabla. OK, this computes nabla squared f equal nabla squared f, which is equal d2f by dx squared plus d2f by dy squared, right? So again, we declare a result, mp.zeros like f, excuse me. And again, on the interior points only, 1 to minus 1. And I will do now fi plus 1 minus 2fi plus fi plus 1, etc. So I'll implement this formula over here. Okay, the central difference for the second derivative in x and in y. Okay, so we will do f from 1 to minus 1. We're starting in the x-axis, so this would be fi plus 1 minus 2fi plus fi minus 1, okay, over delta x squared plus, same thing, so let's go down in line, plus, I'm going to copy and paste all of these and swap the indexing. Okay, just swap the indexing. This is fj plus 1 minus 2fij plus fj minus 1 over dy squared. Return result. Yes? This one is to go to a new line. Yeah, to allow me to separate rather than having like just one long, yeah. That's neat, yeah. Yeah, you get the long lines, it gets really annoying. Okay. But yeah, thanks for following through. It's super helpful. Easy to make mistakes with these things. Okay. So now for the x momentum, I just need plus nu times Laplacian of u with dx dy, right? Because that is going to be this term, del squared u. Nu times del squared u, correct? And for the y momentum, plus nu times Laplacian of v dx dy. Oops, dx dy. Okay? Okay. Well, I think that's good progress, right? There's, Laplacian. Yeah. Do you mean? So fi plus 1 minus 2fi plus fi minus 1 over fj plus fj plus 1 minus 2fij plus fj minus 1. All good? Okay. We can actually test this right now. So right now we just have advection diffusion, right? No pressure. So we can actually test this now, excuse me, and just try to advance the flow. Let's see what happens. So if I say u is equal to u plus dt times u right-hand side, and v is equal v plus dt, so I'm updating on the spot because this is a 2D problem, etc. I'm not going to store, unless I'm doing an animation, I'm not storing all of these arrays in time or even un or u. I'm just updating on the spot, okay? So I don't have a u new and u old and un. You can do that. That's up to you. But for this case, let's just do this on the spot now just to see what we have, okay? So I can run this now. And let's see if it just runs. Okay, it runs at least, no errors. It did 2 time steps. It's not gonna look okay at all, but let's see. So let's do a quick vector plot. So with the vector plot, you can do plt.quiver and just give it u and v velocities, the 2 velocity vector fields, and it's just doing nothing, right? It's just moving the top wall correctly, but the flow is not what we expect it to be, right? So let's move it a few more time steps. Let's say, 4,000 time steps. Okay. Why is the flow not turning? No what? More importantly, yes, no, how does the pressure turn the flow? Why does it turn? That's fine. It's fine. Why does it turn? I said it when I was talking. So the flow is going to hit the wall. Okay, this flow is going to hit the wall. Why would it need to turn? To conserve mass. Otherwise, it's just going to diffuse and go away. But if you want it to conserve, once it hits the wall, it needs to turn. That's, in fact, the rotation is occurring because of mass conservation, which is creating a different pressure gradient through the pressure gradient, but because of mass conservation. The flow wouldn't turn if there's no requirement for mass conservation. It would just hit it and diffuse. So what's happening here, it is the flow over here is sensing that there's zero over here, and it's just kind of diffusing back. Okay? So as it approaches here, it slows down so that it dies out here. Okay? Because there is no mass conservation. Because there is no mass conservation. Mass conservation is going to create the right pressure term to make it turn. So now we're going to take this velocity field, which is not mass conserving, and we're going to add a pressure gradient to it, the correct pressure gradient, to make it turn. Okay? So now we start building the pressure Poisson equation. Okay? So technically, these would be U tilde and V tilde, right? So these are the tilted velocity fields, in the slides, right? So these are the ones that don't have diffusion, don't have pressure gradient in them. Okay. Build pressure Poisson equation. All right. So for the Poisson equation, I need the right-hand side of the Poisson equation, excuse me, and I need a Poisson solver, all right? So if we go back now to the projection, I have all the ingredients that I need. Where is that formula? Where is that formula for the pressure? Yeah, so I'm going to take this formula actually here. Okay. I have all the ingredients that I need. Let's go this one here. We already computed A and D. Agreed? And we have UN already, which is the all. So I need a divergence operator to apply it to those terms. So let's do this as a routine as well. So we will do a divergence operator. Now the divergence operator acts on a vector field. So I need two components for the divergence operator to work, right? Two fields, two arrays, divergence. And I'm going to do u, call it just uv, or component 1, component 2, and dx and dy, right? Because this is going to do du by dx plus dv by dy, or da by, whatever u and v are. It doesn't matter. They're just two components of a vector. Okay? And I'm going to return, now check this out. dx, I already have everything set up for me. U dx plus d dy, v dy, right? Already declared routines for the first derivative. So I can reuse them to compute the divergence of any vector. Okay? Okay, great. So let's run this cell. You need a minute here. Divergence of a vector field. Okay, so let's call the vector field components A and B, right? Or A and B, right? What's the divergence of the vector with components A, B? Is dA by dx plus dB by dy. Div vector is d component. Yep. Okay, I just call them U and V for simplicity, right? Okay. But they could be any vector, okay? All right, so now we start building the pressure Poisson equation according to that formula that I have. Okay, now the best part is I already have all of those ingredients set up for me. So this whole thing over here, A and D, right? Those are the right-hand side components of the x momentum and y momentum. So the x component, so this is a vector. It has two. This is think of it as a column vector. It has two rows in it. The first row contains advection for x momentum and diffusion for x momentum. The second one, advection in y momentum plus diffusion in y momentum, which we already built as the right-hand sides, right? So those are my two components for this term here, div minus a plus d, right? So all I have to do now is pressure right-hand side is equal to div of u right-hand side and v right-hand side dx dy. Agreed? Okay. So that gives me this term, right? That gives me this term. Because the x component of this vector, so this is a vector containing the x momentum right-hand side and the y momentum right-hand side. The divergence of that is div u right-hand side by dx plus div v right-hand side by dy. I'm still missing one more term for the pressure right-hand side, and that's div un over delta t. Okay? So let's add that and say div of u v dx dy over dt. Okay, so that gives us the pressure right-hand side. Okay, so now we have the pressure right-hand side. Now solve the Poisson equation for the pressure. Now, if you did this on Tuesday, you should have codes for computing for doing the Poisson equation. Okay, you should have code for doing the Poisson equation. Let me grab that real quick. And if you don't, do you all have that code? You don't? Okay. You do have it? Yes. Okay. So let's send it over Canvas, whichever, Jacobi or Gauss-Seidel or SOR. Just send one of them. And I'll show you what we need to fix in that. So in class, you did something similar to this with Maher. He did a fantastic job covering all of this stuff. He fixed a lot of mistakes I had. So you did something like this, okay? So I'm going to copy this. That's the code you will get, something similar to that. And we're going to fix it over here. We're going to call this Poisson solver. Poisson solver. And it's going to take some pressure, dx, dy, and some right-hand side. Okay? I'm going to paste this over here just as is. All right. You set a tolerance and an initial error, a maximum number of iterations, an iteration counter, and we had this alpha or beta for successive over-relaxation. Let's call it beta. And we looped over the interior points. Now, for this problem, we are going to have Newman conditions except at the top wall. So I'm going to start with the top wall. And I'm going to say, so forget, just wait a minute here. OK, if you have the code, just copy it and try to work through it with me over here. So for the top wall, that's the last index in y. Okay, and that's going to be 0. We're going to fix that condition. I'm actually out of time, so we can continue on Tuesday if you want, or we can spend another 10 minutes here.
I really want to see where this
You're going to see where this goes. OK, let's. All right, I'm happy to do that. OK.
I mean, if you gotta go.
No, I don't have to. OK, I'm just I'm happy to stay. Yeah. OK. So now if you go with the so for the bottom wall, we had a Newman condition, which says that dp by dy is equal to 0. In other words, p interior minus p at the boundary to a first-order approximation over delta x equals 0, which means p interior or p boundary is equal to p interior. Okay, so that makes the gradient to a forward approximation equal to 0. So that's a good Newman on dp dy, bottom wall. Same thing for the left wall. I had a bunch of things over here. Let me just delete them. Same thing for, so for the left wall, that's in the x-axis, all dp by dx is equal to 0. dp dx is equal to 0, right? So Newman on p, not Newman on dp dy. So Newman on p dp by dx equal to 0. It means p interior minus p at the boundary is equal to 0. And then finally, on the right wall, let's clean up over here. Okay. On the right wall, we also have dp by dx is equal to 0. Now, this says that p boundary minus p interior is equal to 0, which means p boundary is also equal to p interior. So this would be p, then all y minus 2, right? So p last index in x is equal to the first interior point at the end, okay, on the right-hand side. All right, then we created this, pk value, and you had this loop. Now, there was a typo. There was a mistake that I committed in those slides. I was missing a negative sign in front of the source term. So if you were to go, let me show you the slides and show you where that mistake was. And I will update the slides and just upload everything. OK, so let's see. Keynote. Let me show you the error that I made last time. It's very, very minor error. It had to do with this formula. So there should have been a negative sign in front of the source term, okay, here, minus whatever this is times Sij. That's it. That's the only typo. So in your code, you might pause this later and just kind of go through it, follow with me on YouTube, and just type everything. Just make sure you have a negative sign over here. We don't have our source term is simply the right-hand side, which is this right-hand side function that we're passing. Okay, so this is going to be a very slow solver. Okay, this is going to be a very slow solver. This is going to be a very slow solver, but it's okay. It's gonna do the job. Okay, it's going to do the job, and just goes and iterates until we hit a tolerance of 10 to the minus 5 and up to 50 iterations at most. Okay. So that gives us the Poisson equation. We need to return something. I'm just going to return an error. Return error. Okay, you can return nothing, but I'm going to return my final error after I've done iterating. Okay, and that should be outside the loop. Okay, now why did I not return P? Because P is declared outside, is declared over there. And I'm passing it here by reference, not a copy of it. So it's going to modify the P that I pass from the calling routine over there, right? So I don't have to declare a new one and create new memory. It will just change the values in place. Remember, we declared P over here, and I'm just going to reuse this P over and over again. Okay? So let's kill the kernel and restart this and see what happens. Okay? Now we have the P right-hand side set up. Solve the Poisson equation. Error is equal Poisson. Okay, it took it at least P dx dy, pressure right-hand side. Okay, we're not done yet. Now we have P. So after this, we now have a legit pressure. Okay, now we need to do dP by dx and dP by dy. We're not done yet. Okay, so simple. dP dx is simply d dx of P. So you see how useful that routine was? And ddy was dpdy was ddy on P and dy, right? So because I need those in the x and y momentum equations. And now finally I can do my time update. Finally do the time update. And then say u is equal u plus dt times u right-hand side minus dt times dp dx, right? And v is equal to v plus dt times v right-hand side minus dt times dp dy. Agreed? So those were the terms in our discretization. Okay? And that's it. All right? Okay, let's run it. It crashes. Okay. So invalid index variable. Of course, it has to ruin my day. Has to ruin my day. I know what's going on. Sorry, no need for beta. I'm reusing the same right-hand side. Let me just call this S right-hand side. Sorry, I used the same name here as the other one. Never mind. Okay, just put an underscore. Underscores fix everything. Okay, so it's running now. It's going to be very slow. That's okay. I want it to be slow on purpose so we can learn about iterative solvers later. It's going to do 4,000 time steps. We could have done successive over relaxation to make it a little bit faster.
So successive over relaxation would be increase your beta?
Yeah, go like one. There's actually a faster, so when we say fast, there's two meanings. Is it going to converge with less iterations or less wall time? Okay, so this one, if you go successive over relaxation, it will converge with less iterations, but not necessarily less time. There's in a vectorized version of this where we use array slicing to implement the Jacobi solver. We will do that on Tuesday, which is faster than all of them in wall time, not in iteration count. That's, to me, in the end, what really matters. Okay, so I'm going to go ahead and do maybe a couple hundred time steps. I'm going to restart it. Okay, we'll just do a few hundred time steps just to show you that this is working. Okay, maybe. Okay, so let's do 100 time steps. Okay, what do you think is going to happen? Oh, look at that. It's starting to turn. Okay, do you see? Do you see how it's starting to turn over here? Do you see how it's starting to turn over here because of that pressure field? Okay, so now if you plot the pressure, PLT dot contour F, we have XX, YY, and P. So now you see what's happening with the pressure over here, how it's causing the pressure difference so that it changes the flow so that it conserves, it's trying to conserve mass. Let's run a few more iterations here. So I'm going to comment this out, keep running this. So as I keep running it, it's going to start creating, so let's do 100 time steps. That's 100. So remember, it's going to keep updating from the most recent values. So we should see that recirculation grow larger and larger, guys. Look at that, right? We're actually doing CFD. This is your first CFD code. So we can superimpose this on velocity magnitude if you want. So let me just do that. We do velocity is mp dot square root of u squared plus v squared, right? And we will do plt dot contour f x x y y velocity. Didn't do the quiver on top of it. Hold on. Quiver array location is cxxyy. All right. So look at that. So this is the speed. The color are speed. Let's change the map. Let's do cmap is equal to hsv. All right. This is a little bit better. Okay. So this is colored by plt.colorbar. Okay. So yeah, the it's a kind of weird color bar actually. This is not the corresponding color bar to HSV. Seriously. Okay, red is high, blue is low, right? And they're moving, So let's color them as white. Color equal, let's see, W. Yep. So you can see them now. They're moving. You keep running this, another 100 times steps. Oh, that was fast. Okay, they're going to keep moving, and that primary vortex is going to start forming. Okay? And that is CFD. In your project, you're going to take this code and add conjugate heat transfer to it. So we're going to add a natural convection problem. We're going to heat one of the walls and cool the other one, and we're going to affect the flow. So it's going to be driven by the driven cavity from, yeah, so it's going to be driven by the cavity over here, and we're going to heat this wall so the flow goes up. So there's going to be a competition between the flow trying to come down and the flow trying to go up. It's going to create some interesting structures. But you guys just did CFD today, okay? Can I give you one punchline before you go and to disappoint you? To disappoint you very well? Okay. So in the end, we did all of this to satisfy mass conservation. Should we check for that? Yeah. Okay. Div u is equal div uv dx dy. Okay. plt dot, I like to do the image show so we can see in pixels. Im show div u, and I'm going to put the origin at the bottom, so lower. It's huge. 6, whatever, meters per second squared. That's huge. It is not divergence free. It's trying to be divergence free, but it's not divergence free, unfortunately. And we will see why on Tuesday. But this is as close to a CFD code. You know, it's a little bit divergence free. For the most part, it is divergence free. But here it's not. There's going to be more and more regions that are not divergence free. And this has to do with the fact that we're using finite difference method. And we will demonstrate on Tuesday, it is because div of the gradient of the pressure is actually not equal to the Laplacian of the pressure. Div grad is not equal to del squared. That's why we need the staggered grid. So I will prove that to you on Tuesday. But still, this is your first CFD code. It's okay. It tries to conserve mass a little bit. It's better than no pressure at all. And we will use that for our project, okay? Because the finite volume is going to take us some time to develop the code for that. But there you go. As promised, fifth lecture, CFD code, first work in CFD code. For those who didn't follow, please go through the YouTube. You have to implement this with your own hands. You don't do CFD if you don't write your own CFD at least once. Okay? So if you were just kind of trying to absorb this here, which is great, go at home, take your time, and repeat every step I did and think about it.